So we are going to solve this problem using Thevenin's theorem. That is, find current through RL using Thevenin's theorem, where RL is 2 ohms as mentioned in the circuit. Okay. So first step, what is the first step? We can find a VOC, open circuit voltage, or VTH. This is also called, right? Finding VOC or VTH. Okay. So what is the procedure? Open circuit the terminals of A and B, right? So I will redraw the circuit here. After open circuit, the circuit will look like this. Okay. So these are the terminals A and B, open circuited, right? So 2 ohms, 4 ohms, 15 ohms, 3 ohms, and 5 ohms. Okay. And what do we find out? So VOC or VTH. Right. So how do you find out VOC here? So let us take the polarity as like this, plus and minus. Okay. And the polarity of the voltage across these three resistors is plus and minus, and this is plus and minus, and this is plus and minus. Okay. And let us apply KVL to right side part of the circuit. Okay. So if you apply KVL to the right side part of this circuit, uh, let us take a direction, right? Clockwise direction. KVL in clockwise direction. Clockwise means what? So in this direction. Okay. So if I apply KVL in this clockwise direction, what happens here? I will start from 3 ohms, right? So plus, sorry, plus V3 ohms plus VOC plus V5 ohms minus V15 ohms is equal to 0. Is it clear? So VOC is equal to V15 ohms minus V3 ohms minus V5 ohms, right? But it is a open loop, right? It's not a closed loop. So V3 ohms is equal to V5 ohms is equal to 0. Therefore, what happens? VOC becomes equal to V15 ohms, right? So V15 ohms is how much? That means are you able to understand? See, the voltage across 3 ohms and the 5 ohms is 0 because there is no current flowing through 3 ohms and 5 ohms, right? But in 15 ohms, it is common to the right side part and left side part. So obviously, there will be some current flowing through the 15 ohms. That may be the current that is flowing through the left side loop of the circuit. Is it clear? Hello? No one is there?
No.
Right. So V15 ohms, V15 ohms. How to find V15 ohms? I will draw the circuit once again here. Here it is plus minus 20 volts. So this is 15 ohms, this is 2 ohms, this is 4 ohms, right? So simply using so V15 ohms, V15 ohms is equal to voltage division rule, right? Because 2 ohms, 15 ohms, and 4 ohms. All these three are in a series. So we can apply voltage division rule. That is total voltage into 15. That means the resistance across which we want to find out voltage divided by the sum of all all the resistors that are in series, right? So 15 plus 6, so it is 21. So how much is this? You tell me. అంత వాల్యూ ఎంత? 14.28 volts. Okay. Somebody has said. So 14.28 volts or 14.3 volts, right? So VTH we have found out, right? So VTH is equal to 14.28 volts. Now finding RTH, right? To find the RTH again uh, we have to keep the terminals open circuited and replace all the sources with the internal resistance, right? So I am drawing the circuit. So these are the terminals. So these are the terminals A and B, and we have to look back into the terminals, right? But what is the source here? Huh? The source in the circuit is an ideal voltage source with internal resistance Ri is equal to 0 ohms. So you have to keep a 0 ohms here. So Ri is equal to 0. This is 2 ohms, this is 4 ohms, this is 15 ohms, this is 3 ohms, this is 5 ohms. Right? Now look back into the circuit from terminals A and B. Okay. Now then RTH. ఏమవుతుంది? What will be the RTH? First, on the left side loop, you have 2 plus 4, 6 ohms parallel, right? So, 2 plus 4 in series, right? 2 plus 4 ohms parallel with 15 ohms, right? So here, right? So
Yes.
that's equal to 6 into 15 by 21. How much is this?
4.8.
And the
4.28. 4.8.
4.28. 4.28 ohms, right? Now, is it clear? 2 and 4 are series, and combinedly they are together, they are in parallel with 15 ohms, right? Because this is a node and one node and another node. Between these two nodes, node 1, node 2, between these two nodes 15 ohms is there. And similarly, and the combination of two series combination of 2 ohms and 4 ohms is also connected between these two, right? If you replace 2 and 4 with a single 6 ohms resistor, you can easily identify, right? So anyhow, I am drawing it here. This is 2 plus 4, okay, like this. Now for this circuit, now the circuit has become uh, like this: 5 ohms, this is 4.28 ohms, this is 3 ohms, A and B. So RTH is equal to how much? 8 plus 4.28, 12.28 ohms. Is it clear? Now our circuit became a Thevenin circuit, Thevenin's equivalent circuit. Our Thevenin's equivalent circuit is Thevenin's circuit becomes, what is the voltage? 14.28 volts, right? So it is 14.28 volts in series with the RTH, 12.28 ohms. Now these are the A and B terminals, A and B. So what is the resistance we kept there? What resistance we kept there? 2 ohms, right? The resistance, load resistance was 2 ohms, right? So we connect 2 ohms here. Okay. Now current. Now I2 ohms is equal to, how to find out this? Hello. 14 2 12.28 and 2 ohms are in parallel in series. So I2 ohms is 14.28 by 2 plus 12.28 total resistance. This is 1 ampere. Luckily we got a round figure, 1 ampere, right? Anybody who can respond and speak, right? Also remember said the current is 1 ampere. He has calculated. Okay. నా స్క్రీన్ క్లియర్గా ఉందా మీకు? పైన ఏమైనా అడ్డుగా కనిపిస్తున్నాయా?
సార్ బాటమ్ లో కనిపించట్లేదు.
బాటమ్ కనిపించట్లేదా? ఇప్పుడు ఏమైనా కనిపిస్తుందా?
ఎస్ కనిపిస్తుంది.
Is it clear?
ఎస్
Right. Next we will go to Norton's theorem. Shall we go?
సార్.
So one more important announcement I want to make to you. These are duals. Thevenins theorem and Norton's theorems are duals. Okay. Okay. The announcement is uh, right. Now here for this Norton's theorem and Thevenins theorem both are duals. Okay. Now the same problem which we just solved, I will solve using Norton's theorem. Right. So according to Norton's theorem, you can replace any complicated network. Uh, we can replace any complicated network into a simple network similar to the Thevenin's theorem, but it will have a current source, Norton's current IN, in parallel with the Thevenin's resistance. Okay. In Thevenin's theorem, what we did, we will calculate open circuit voltage, right? See, VTH is nothing but VOC. Okay, and we used to calculate Thevenin's resistance, keep it increase with the source, right? This is Thevenin's, this is Norton's theorem. Okay, so these two are dual circuits, duals. Okay, because the relation between IN and VTH is Norton's current IN and VTH is IN is equal to VTH by RTH. That's it. Or VTH is equal to IN capital M, right? IN into RTH. Okay, this is nothing but source transformation only. So this was possible because of source transformation. You can convert a current source with its internal resistance like this, right? Say for example you have a current source like this with its internal resistance Ri. Okay, say some I source Ri. This can be converted into a voltage source in series with voltage source will have its internal resistance plus minus V source, right? This is Ri. Okay, so Is is equal to Vs by Ri. This is the relation. So later we see, right? Source transformation is also there in this with right uh, module. Okay, this is source transformation. Using source transformation also we will solve problems. My screen is not clear. Someone
Bottom
has
part is not clear.
not clear or not at all visible.
Bottom part
Not
not
at all
visible.
visible, sir.
కనిపించట్లేదా? Up to which part?
Bottom part, sir.
What is the last line you see?
Up to formula, sir. In is equal to V by R.
Okay, okay. So using source transformation, if you have a current source like this, a current source Is with its internal resistance Ri, this is the practical voltage source, right? And you can convert this and back into this. This is V source Ri, terminal 1, terminal 2, terminal 1 and terminal 2. Where the relation between these two is 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 equal to Vs by Ri, or Vs is equal to Is into Ri. We can simply convert a voltage source into current source and quickly convert a current source into a voltage source whenever it is required while solving the circuits. Okay, this is nothing but source transformation. This is also this was possible by source transformation. Source transformation. Now the screen is clear. Hello.
Yes, sir.
I-
Clear.
Is the screen clear?
Yes,
Yeah,
sir.
yes, sir.
Now let us take our previous problem, right? Let us solve the same problem using a Norton's theorem. The problem we took is, what was the problem? We had a voltage source with 2 ohms resistance, 4 ohms, 15 ohms, 3 ohms, and 5 ohms, 2 ohms, right? So the terminals are A and B. Question is, find current through RL using Norton's theorem. Okay. So finding RTH is same. Same. So RTH is equal to 12.28 ohms. Just we have solved the same circuit using Thevenin's theorem. So whether it is Thevenin's theorem or Norton's theorem, solving RTH is same procedure. Okay, is it clear?
Yes, sir.
So still the bottom is not clear, huh?
Sir, up to RTH is equals to 12.8. It clear.
Nothing I have written beyond that. Okay, right? So let us find IN, Norton's current, right? So finding Norton's current. So for this, we have to keep the terminals not open but short circuit. The voltage source is how much it is? 20 volts, right? So this Norton's current is nothing but a short circuit current. After short circuiting this, how much current will flow here? That is what Norton's current. So this is the resistors are as usual. Okay. So you have to previously we used to find out VOC instead of VOC we find ISC here. ISC is nothing but I Nortons. ISC here in Norton's theorem. Okay. So how to find out? See, this are 0 ohms, 3 ohms, and 5 ohms are in series. Okay. So they are in series, right? So let us solve it using a nodal analysis. Let's find ISC using node analysis. Okay. So the nodes are node 1, node 1, node 2. Okay. This is node 1 and node 2. Right. Uh, let us so let the voltage at node 1 be V1. Okay. Let node 2 be reference node. Okay. Now, and assuming the let us assume the currents, right? So because there is no current source here, right? So let I1, I3, I2. Okay, three currents are there. So KCL at node 1. I should have drawn the big circuit. Anyhow, I will draw here a big circuit here. Sorry.
Sir, diagram right side part is not clear.
Not clear.
Yes, sir. After 3 ohms and 5 ohms, right side.
Okay, okay. I will, I will clear it. Now is it visible?
Yes, sir.
IN. Now it is clear. Is the screen moving?
Yes, sir. Yes, sir.
Okay, okay. So that is the problem, right? So this is 3 ohms, 15 ohms, 2 ohms. This is 4 ohms, 20 volts. And the node is here. The node here is a N1, right? So here we have I2, I1, I3. So KCL at this node gives us a uh, I1 plus I2 plus I3 is equal to 0, right? Now what to do? I1 is what? And రాస్తాను bottom line కనిపిస్తుందా? Okay, I will write here. I1 is how much? V1 minus 20 by 2. I2 is V1 by 15. I3 is nothing but IN, that is equal to V1 by how much? This is 5 ohms, right? 8 ohms. Okay, so therefore V1 minus 20 by 2 plus V1 by I think these equations are clear, right, to you,
Yes,
is equal to 0. Okay, V1 minus 20 by 2 plus V1 by 15 plus V1 by 8 is equal to 0.
sir, equations are not clear. Bottom of I3.
I3 తర్వాత anyhow I will write it again in the next slide. So V1 minus 20 by how much it is? Not 3, it is V1 minus 20 by 2 plus 4, 6, right? 2 plus 6 plus V1 by 15 plus V1 by 8 is equal to 0. So in this previous one I have to erase this one. So this equation, this is 2 plus 4, 6. Okay, so solving this, 1 by 6, 1 by 15 plus 1 by 8 is equal to 20 by 6. So how much is this? చెప్పండి ఎంత? క్యాలిక్యులేట్ చేస్తున్నారా? 43 by 120. Forty-three V1 by 120 is equal to 20 by 6. Okay, so V1 is equal to 20 by 6 into 43. How much is this? 9.3 volts. So the current, the voltage V1 is 9.3 volts, right? Now ISC is how much? ISC is nothing but I3, that is V1 by 8. So 9.3 by 8. How much is this? 1.16 amperes. Now I 2 ohms. In our previous circuit, the previous circuit is what? This is the previous circuit. Current in the 2 ohms we need. So this is RL is 2 ohms here, right? So in 2 ohms the current must be found, right? We have to find out current in 2 ohms. So the circuit, first let us construct the Norton circuit, right? So Norton circuit is 1.16 amperes. RTH is how much? Sorry, the Norton circuit must be parallel, right? RTH is 12.28 and 2 ohms. Okay, so a total current of 1.16 amperes comes up to here. So 1 point, so 1.16 amperes comes here. This is IN. Some current flows into this, right? So not IN, sorry, I2 ohm. I2 ohms is equal to IN. This is IN. IN is IN into other resistance 2.28. This is simple current division rule. Plus 2. When these two resistors are in parallel, we can use the current division rule, right? So 1.16 into 12.28 divided by 14 point. Wait, I think we must get 1 ampere here. 1.16 into 12.28 divided by 14.28. Got it? 1 ampere. Babu, clear? Is it clear? Hello?
Yes, sir.
So in Norton's theorem also we got 1 ampere, just like a Thevenins theorem. Okay, once you calculate a Thevenin's equivalent circuit, you can just simply convert it into Norton's equivalent circuit just using this source transformation only, right? Which we have discussed in our previous slides. Okay. Okay, na? Now, is there any doubt? It's already 1 o'clock. I have taken 10 minutes more today. Anyhow, tomorrow we will be having a exam 9 to 10, right? Tomorrow morning, some first hour is ours, huh? Hello. Hello. Okay. So most of you have left. Only 45 people are there, and no one is responding. And already time is up. Okay. Just a second. So what happened? If you have any doubt, you can ask me. Are you checking for a timetable? Tomorrow we have in the afternoon, I think 1 to 2. Okay, anyhow, I'll check the timetable. We have some posts in chat. 2 to 3 class. Okay, okay. But exam is 9 to 10 only, no? Okay. Hmm? So up to whatever the syllabus is covered in the first module, up to that only we will have exam. Okay. Wish you all the best. If you have any doubts today, you can ask me later also. Okay, then I will end this session. Right. So please uh, see this YouTube channel